Okay, let's get started. Let me share my screen. Can you see my screen?
Yes,
Dr. Ali.
Okay. So, I mean, in last class, although we are looking those electric components, basically the electric machines, but I think I could not cover the synchronous generator, synchronous motor, induction generator, and induction motor. So those four components, first I'll be covering, and then I'll be starting the power system stability study. Uh, as you can see, I have just written briefly, just at a glance. Synchronous generator, it has armature or stator on which the coils should be wound or mounted. And then there is DC field rotating, which is
excuse
opposite
me,
to
sir.
the, sorry, Venkat,
Your voice is breaking, sir.
you could not hear?
Yeah, it is breaking.
Okay, maybe some internet issue. Can everybody hear clearly?
Yes, Dr. Ali, for us it is clear.
Yeah,
Yeah,
I'm
it is
good.
clear for me too.
Oh, okay. And Venkat,
Yeah, now it is fine, sir. That's it,
maybe
sir.
there is some issue with your laptop or computer, whatever.
Yeah, yes, sir.
Because I can hear each of you well. Yeah.
Yeah, now I can hear, sir. That's okay.
Okay, thank you.
Yeah.
And see that, as I told, this is opposite to the DC generator. In case of DC generator, we discussed that DC field remains static and the coils together with the armature that moves. But in this case, it is opposite. You see, I have written armature or stator wound with coils and then DC field rotating, and right side I have written the rotating speed, synchronous speed, ns 120 f over phi. This is the amount of speed. Now, uh, and then I have written couple of things, and then I am going to that whiteboard. In case of permanent magnet synchronous generator, the DC field is permanently magnetized. Now, the DC field, as I mentioned last class, you have to magnetize it with the help of DC excitation, with the help of DC source. So this is the conventional or traditional generator practice. But there is new concept which is called permanent magnet synchronous generator. In that case, that is permanently magnetized, for example, about 30 years or 35 years. So you don't need any extra or additional DC sources. You don't need any DC excitation. That's the difference. So many times you will be seeing PMSG, permanent magnet synchronous generator. And then I have mentioned the type like salient fold, then non-salient fold or round rotor type machine. And I have written couple of features. So therefore everybody, let's have a look at the whiteboard that will help you understand much more. Uh, I think you can see the whiteboard, right? Yes. Okay, so in case of synchronous generator, for example, this is the body, armature body or stator body. There should be a three-phase coil mounted on it. As you can see, for example, this is A phase, this is B phase, and this is C phase. And in between, there is the rotor circuit to which the shaft is connected. And again, the shaft is connected with the turbine T. Okay. And then this is rotating at a certain speed. Now the magnetic field basically are mounted on the same body. The, for example, here is the North Pole and here is the South Pole. This means in this case, magnetic field is mounted on this body to which the shaft is connected. So this means when this shaft is rotating with the help of the turbine or prime mover, the magnetic field is moving. But you see, these coils, these three sets of coil are static. So remember, in case of the DC, it was just the opposite. In case of the DC, this is the armature body to which the shaft was connected. And if you remember, so I put the magnetic field in that way. So the magnetic field was static. And then the armature body, this means the coil was rotating. That is the case of the DC generator. But this is the case of the AC generator. In case of AC generator, coils on which voltage will build up or you will get power, those will remain static. So there, and can you guess why? That why this, what is wrong if I make the similar arrangement? Like if I connect the shaft system with this body, and again I can put the magnetic field in that fashion. So there is no problem. I mean, voltage will build up, but can you guess that you are rotating? What is the amount of voltage here? As I told you before, line to line RMS voltage is 11 kV, or it could be 13.8 kV. So now you see, if this body rotates, this means if this coil rotates and it is producing so high voltage, 11 kV, 11,000 volt. So therefore, during the movement, it might happen that because of centrifugal force, these coils may be displaced. And also you see, actually in real practice, these coils are properly insulated. So therefore, for B phase is properly insulated with C phase, and C phase is properly insulated. So therefore, and that's why they remain static. Now, if it moves, if you allow to move the coils with the help of prime mover, then because of the movement, anytime these insulations or over the time, these insulations might be damaged. So, and then highly likely that there could be short circuit between any two phases or all phases. So therefore, the reason is it is producing high voltage. Because of the movement, the coils may be deformed, and then insulation might be damaged. To prevent those situations, it is not allowed to move. That's why in case of synchronous generator, coils mounted on the armature body remains stationary, static, and then you have to rotate the field. The thing is that you have to make rotate at least one thing, either field or the coil. That's the voltage generation principle, like Fleming's right hand rule. Everybody know. If both remain static, there will be no voltage. If both moves at the same speed, no voltage. There should be relative motion. Therefore, in this case, what is happening? The magnetic field is moving, but the coils are static. In case of DC generator, because it produces hardly 1 kV, so everybody see, hardly it produces 1000 volt DC because this is for a small scale application. That's why in this case, even though it rotates, but it is not that dangerous. And it is not the three-phase system. There is not so much coils here. That's why traditionally the armature rotates in this case and field remains static. But in this case, because of the high voltage, because of the insulation issue and the coil deformation issue due to centrifugal force, armature is remain static. I think everybody is understanding. And then now this magnet, North Pole, South Pole, I mean, if I draw the circuit, actually it will look like that. You know that because it is filled, basically this is a coil. This is a coil, and you are applying the DC voltage here. That's the thing. So what is the thing? If you apply DC voltage, then DC current is flowing through it. And what is the consequent of the current through a coil? It will produce some flux. It will produce magnetic field. This is the magnetic field or the flux. And this will create the North Pole and South Pole, basically. And then the magnetic field will be excited. So this means you need the external DC source to excite the field. And this is, I mean, mainly the inductance, mainly the coil, but there can be small resistance in it. So that's why there is a small value of R and then mainly the inductance. Now, you see, then this magnet, you have to excite it from external source, and it is DC source. So although all over the world, in most of the power plant, still this is the system. But in order to avoid this DC excitation, external DC source to excite the field, these days, power engineers are preferring PMSG, permanent magnet synchronous generator, meaning that let's permanently magnetize. Permanent means very long time, 30 years, 35 years, or 25 years. If you magnetize this one, then it will run full well. After that, once it live gone, then again you replace or remagnetize it. Everybody, could you follow me?
Yes, Dr. Ali.
Okay, great.
Yes, sir.
Yes, Dr. Ali.
Yes. Okay. So now the thing is that there are two terms, salient pole machine and non-salient pole machine. Now you see, because this pole is rotating, according to the arrangement of the poles, the generator can be two types. So therefore, let me clean all of these things, because I properly saved, so no problem. And in the video, you can see the previous picture, no problem. According to the field construction, it is two types. For example, this is the body. So I am concentrating only the magnetic field and the rotation. Okay, so this is the rotor body, and then like this is moving, and how I can place the magnetic pole. You see, North Pole, and then this is South Pole. It is on structure, and see the other structure here. For example, this is again the same way. The shaft is connected, but see how I am drawing. This is North Pole. For example, there can be South Pole here. There can be North Pole here. I mean, I am placing many poles. Just a moment. For example, there is on South here, or there is on South here. So as you can see, if you look from outside, the lots of magnetic poles are mounted on the outer body, outer rim of this circular body. In this picture, you see that North Pole, South Pole, and typically it is two, hardly it is four, but typically it is two. But in this case, there can be many. It can be 20, it can be 40 poles. Therefore, you need to place those poles, I mean, North Pole, South Pole, you need some space. That's why typically its diameter is larger. Here, because you see, it is placed the way it is placed, it requires less space. So it has the smaller diameter, but it has the larger diameter. Now, the thing is that we are putting many poles here, and we are putting only to our maximum four, the 4 poles here. So why it is like that? What does that mean? And for example, this is the rotation. At a certain speed, both are rotating. So everybody see, you remember the synchronous speed equation as I showed you. So NS, that 120, then frequency over number of fold. Now, you see, what's the frequency in United States? The frequency is 60 hertz. So you all know. Or in like Asian country, it is 50 hertz. So think about United States, it is 60 hertz. Then look this on this figure. For example, you have only 2 poles. Okay, just a moment. Hold on. It looks like it is not. Yes. Okay. Okay. So here you see there are only 2 poles. So therefore, look this equation. If you put pole number 2, and if your frequency is 60 hertz, so what is this value? This value, if you calculate,
3,600.
600, right? 3,600 RPM, revolution per minute. So And then in this case, everybody say, in this case, for example, there are many poles. So if the pole number increase, just look, if the pole number is 4, then this value is getting 1800. So with the increase of the pole number, your speed is getting decreased. So let's say in this case, its speed is 900 RPM because it has many poles, for example. And the equation is the same. This is the equation that is valid for this case also. Because you have to maintain 60 hertz, and you need here, you know that, sorry, you need the 60 hertz, you have to maintain that. So you can change that on. But when you are using the large number of poles, your speed is getting decreased. It is not at this rate. So the question is, and as I told you, this arrangement is called non-salient pole. This arrangement is called salient pole. Salient pole means poles are visible from outside. There will be many poles and poles are visible. Really, if you look from outside, you can see these things. But because this North Pole, South Pole kind of, it is buried inside, so you might not see from outside. That's why it is invisible. It is called non-salient. And because these are visible, it is called salient. So now that's the question that I am saying. Here there are many poles and those are visible. Here are only 2 poles invisible. So what is the motivation? What is the philosophy behind this system and this system? Like,
To
sorry?
increase the EMF.
No, that is not the right answer. I mean, soon you'll be getting that. Okay. And everybody keep in mind, our frequency target is 60. You can't change this frequency, whatever here you are getting lower speed or whatever your pole number is, you have to maintain the frequency because frequency is at the grid level, at the customer side. So because if you change the frequency to match with, to maintain the same RPM, then it is problematic for the customer. So you cannot change that one. So that's why you have to play with this pole number and this. Now everybody say the Manoj that you are answering, you all know the like gas turbine or nuclear turbine, steam turbine. Typically they use this system because you know this shaft is ultimately rotating with the help of the prime mover. So the prime mover is connected here. Prime mover means the turbine. Turbine is connected here, and that turbine can be, the input can be, fuel input can be coal, oil, gas, etc. And typically they have the very high speed. That's why this system is preferred because it rotates higher speed. Here let's say that 3600, and you have to maintain the frequency 60 Hz. So what should be the pole number? You cannot use more than 2 pole here. Now, on the other hand, think about the hydroelectric system, hydroelectric power plant. Typically, because the here is the turbine, and turbine depends on the waterfall, and waterfall naturally has low speed. So therefore, from the hydraulic turbine, naturally you will get lower RPM. Say assume that 900 RPM. Now you are getting 900 RPM, but at the output, look the equation. Here it is 900 RPM. That is coming from nature, from the waterfall. But here you have to maintain the 60 Hz. So what you have to do? You have to increase the pole number. That's why for hydroelectric power plant, you have to choose this configuration. So therefore, now I am answering Manoj to your question. It is the geography that determines the type of the pole, whether non-salient pole or non-salient pole. Because you cannot, at the University of Memphis campus, you cannot place the hydroelectric project because there is no water there. Do you understand? So therefore, for hydroelectric project, you need a specific location. It depends on the geography. It depends on the nature. You need river or the lake, or you have to create dam. So it depends on that. And because the hydroelectric turbine naturally rotates at slower speed, consequently, you have to choose higher pole number. That's why this configuration. And in this case, because naturally the speed is getting very high, to match with the 60 hertz, you cannot but put 2 or the maximum 4. If it is 1800, then maximum 4. So that's why it is not just what is the pole number or what is the frequency. It is the geography that determines the type of the pole, whether it is non-salient pole or the salient pole. So everybody, could you follow me?
Yes, Dr. Ali, I have a question.
Okay.
So in this non-salient type of configuration, we have only like 2 magnets, not more than 2, right?
As I told you, the max, I have seen maximum 4.
4.
So this one, if it is maximum 4 for United States, the speed here it will be 1800. But
And another,
sorry, okay, go ahead.
go ahead, Dr. Ali.
Oh, and in this case, I have seen like up to 40 pole. And then if you like, for example, so I believe everybody is familiar with the Simulink, MATLAB Simulink. If you see the Simulink and synchronous generator property, if you just click on module, you will see that by default, I think pole number 20 is placed there. If you choose this, on the other hand, if you click this module, by default it is 2. Because in most cases, all over the world, maximum like 4 and I mean 90% cases 2. Yeah. And in this case, minimum 4, 6, and then from 4, 6 to upward, up to 20, up to 40, it can. So,
And Dr. Ali, the EMF equation we discussed last time.
yes.
So, I mean, the EMF generator is like almost directly proportional to the poles, because Z phi n by something into P by A was the formula, right?
Yeah. Number of pole divided by A. Oh, that was for the in case
in
of
the
the
DC
DC generator.
Oh, only for DC. Okay.
Yeah, that was for
Yeah.
DC generator.
Okay, I got it. I was confused. Thank you.
Yeah. So in this case, the equation will be kind of equal to 4.445 F Kc Kd, it is called.
Okay.
So sorry, 5Fn.
Yeah.
4.44 N 5F Kc Kd. This will be the equation.
Okay.
Yeah, where N is the number of turns and phi is the flux, amount of flux, F is the frequency, Kc is called the coil span factor, and Kd is called the winding factor.
Okay.
Yeah, so it's different. Okay, so with that, so therefore you all understood that working principle of synchronous generator. Now let's again go back to that slide. We were discussing these ones. You see, here I have written down the property like Manoj, look, salient pole synchronous machine. Poles are visible, low speed, larger diameter. Larger diameter because you have to place many poles, so you need space. See the property of non-salient pole. Poles are non-visible, high speed, smaller diameter. These are the properties. Okay, now three-phase induction motor. This is very important. In most of the industries that three-phase induction motors are used. It has a lot of application. So, and then three-phase induction motor is frequently called the rotating transformer because the principle is the same. In case of transformer, it has primary, it has secondary. And in this case also, it has primary, secondary, although we will be calling stator and rotor. But exactly the working principle is the same. That's why sometimes it is called a rotating transformer. And
Can you make it full screen, Dr. Ali?
Sorry?
Can you make it full screen?
Ah, okay.
Thank you.
Can you see now? Can you see?
Yes, Dr. Ali. Yes.
Okay, I think this is much better, right? Okay, so
Yes.
so therefore in this case also there will be two sets of coil, one on the stator, one on the rotor, I am showing you the picture on the whiteboard. And in this case, the thing is that everybody remember, in case of induction motor or induction generator, there will not be any physical poles that I discussed just now. That salient pole, non-salient pole, those are the physical poles. Those are the real pole. But in case of induction motor, there will not be any physical poles. You have to create pole with the application of the voltage. And once you apply the voltage, because you know this is motor, three-phase motor we are discussing, so you have to apply the voltage. And once current flow, then that will cause rotating magnetic field. And that magnetic field will speed by using the same equation, 120 F over P, where N is called the synchronous speed, F is the frequency, and P is the number of pole or the pole number. So the pole number is determined how you design the coils. But keep in mind, those are not the physical poles. Because as I told you, once you apply voltage and current flows through any coil, then it creates a magnetic field, north pole, south pole. So therefore, these are not the physical pole, but those magnetic poles rotates according to this speed equation. So, and then the voltage build up on the secondary coils, that is the rotor circuit. And if it is connected, I mean closed circuit, then that will produce another sets of flux. And there will be interaction between the main field flux and that flux. Consequently, torque will produce and motor will start rotating. So, I mean, soon I am showing you. And then I have said always draws real and reactive power. And there is one term, it is called the slip. Slip is Ns minus Nr over Ns, synchronous speed minus rotary speed over the synchronous speed. And slip varies from 0 to 1. And slip speed definition is synchronous speed minus rotary speed. You see here it is just one slide, but like it is covering one full chapter that may consist of 20, 30 pages. So everybody see. So therefore now I am explaining, this is very, very important. I mean, that's why everybody see, this will help you a lot when you will design any power network, including induction motor as a load. Just this conception will help you a lot. So just see again the whiteboard. Okay, because I have already saved. So let's clean off everything. Okay, so let's start. We are discussing the three-phase induction motor. Everybody see, this is on body, and then this is another body to which the shaft is connected. Okay, and this will rotate later. So on this body, three-phase coils are placed with 120-degree apart. So therefore, because we are discussing the motor, so on the stator body, we will apply three-phase voltage. So therefore, see the direction. I am applying the three-phase voltage. For example, VA, and then VB, and then VC. Consequently, the current is flowing IA, IB, and then here IC. And then there are another set of coil on this body. This body is called the rotor body, to which the shaft is connected. So still the shaft is not rotating. Initially the shaft is starting. Now everybody see the operation. Once you apply the three-phase voltage, and in other words, the three-phase current is flowing through three sets of coil. What is the application? What is the consequence of flowing current through a coil? They will produce flux. So therefore, this is producing flux here. This is producing flux here. Similarly, this current is producing flux here. And if you sum up, if you combine on three sets of flux, then you will look really, they are rotating. They are moving. They are rotating. And that rotation speed is that one, exactly the same equation. 120
Synchronous.
F over P. So therefore everybody say this speed is not the safety speed. This speed is called the synchronous speed.
Synchronous speed.
Sorry?
Synchronous speed.
Yeah, synchronous speed. This speed is called synchronous speed, but everybody, this speed is the rotating magnetic field speed. This is not the speed of the shaft. Still the shaft has not been rotated. Everybody keep in mind, I mean, don't mix up. This is the synchronous speed of the rotating magnetic field, which was built up because of the application of the voltage. Now everybody see, initially these coils, these three sets coil, this body is static, it is not rotating, but we got a rotating magnetic field. So you see, as I told you, the voltage generation principle is that either the coil should move or the magnetic field should move. In this case, we got rotating magnetic field. Initially, these coils are static because the shaft is not rotating. So voltage will build up on these coils. Once voltage are built up, so let's designate this is like A prime, and this is B prime, and this set is C prime. So once voltage will build up, then consequently there will be current. And if the current flows, then what will happen? Again, there will be another set of magnetic field here. There will be another set of. So therefore, let's designate this is phi r. So the initial set, this let's designate this is phi s. This means magnetic field or flux of the stator, and this is magnetic field of the rotor. Now there are two sets of flux, one is phi s and other is phi r. There will be interaction. They will interact each other and hence produce the torque, and consequently this shaft will start rotating at a speed. Let's say this speed is nr. So therefore see the difference. Now I have designated by the symbol nr to indicate that this is the rotor speed, because this body is called rotor. But I defined this on by the symbol ns, synchronous speed, which is the speed of this magnetic field. So now say, then motor will start rotating. This shaft will start rotating at a speed nr, but there must be some difference between ns and ns. Ns must be greater than nr. Otherwise, motor will stop. So see, therefore everybody see why I said that ns must be greater than the nr. Because if you see, if both are equal, so this means what will happen? Next time, there will not be any voltage built up. As I told you, the condition to produce voltage, there should be relative difference in speed. Either the magnetic field is fully stopped and coil is moving, or coil is moving, other one is stopped, or there should be relative difference. That's why if both have the equal speed, the next time, because there is no relative motion, so according to Fleming's right hand rule, there will not be any voltage buildup, there will not be any subsequent fire flux, there will be no interaction, no torque, ultimately motor will be stopped. So therefore there must be the difference, and typically the ns is greater than the nr. So therefore that difference is called the slip speed that you look in the previous slide. It is called the slip speed. Slip speed means it is not like that you fall down or slip. It's just because the rotor field lagging behind than the stator magnetic field. That is the meaning. So this means because first you are applying voltage here, consequently phi is being developed. So it has higher speed than the NR, because NR speed is dependent on that phi s. If you see, if you don't apply voltage, there will be no phi s. Consequently, there will be no fire, no interaction, no torque, and hence no speed on the shaft. That's why in this case, NS is dominating over the NR. But NR is the actual motor speed. Now, if you use the term motor speed, that is the NR, that is not the NS. Keep in mind, this NS is only the magnetic field speed, not the actual motor speed that you can use for any application. So NR is useful. You can use NR. So sometimes it is called motor speed, sometimes called the rotor speed. And NS is always it is called the synchronous speed. Now, there is one term which is called the slip. So therefore the slip is in the numerator, that slip speed. You see, the NS minus NR, and in the denominator it is NS. So everybody see. So now we answer, for example, at the beginning when the motor has not started rotating, what was the value of the slip?
Slip would be 1.
Yes, because the NR was 0, because NR was the speed here on the shaft. So as I told you, that is the thing I am emphasizing from the beginning, because this is motor, you are applying voltage. So definitely initially the shaft is not rotating. This means the shaft was at standstill condition. So NR was 0. And then once the motor is rotating, then there will be some different. So you will be getting some positive value. So now when and then if NS equal to NR, then what is the value of slip? That is the 0. So that's why slip varies between 0 to 1. So 0 means stop, 1 means stop. So therefore the motor operates somewhere between, typically 0.5, 0.6. At that value, motor operates well. Everybody, could you understand the range of the slip? It varies 0 to 1. So when it is 0, when NS become equal to NR, so 0. But even though the speed becomes 0, I mean the value can be this, but it's still like you can apply and it will produce the, you will get the NS. So we are talking about the NR. And then when NR is 0, like at the beginning or motor is stopped, but still, for example, you are applying voltage, still it is producing the flux, and that is the NS speed. So NS over NS is 1. But at that time, the shaft is not rotating. So therefore, when the slip value is 0, that time motor is not rotating, it is stopped. When the slip value is 1, at that time also motor is not rotating. That's why the range is between. Now, everybody say, now come back to the condition, look the slip equation, the range. Now, for example, I connected a turbine here. Everybody see, this shaft, and I connected a turbine here. For example, I connected a wind turbine. So what will happen? This motor was running, so it was running at a certain speed, but then I connected additional source of rotation, which is wind turbine. So what will happen? The speed of the motor, it will increase, right? And then look the equation slip. Now, if you can make this thing like NR is greater than NS, if you can make this situation, so then what you are getting, what will be the slip value?
That will be induction generator.
Yeah, slip will be negative. You will get the negative value of the slip because your NR is greater than NS. In that case, like slip, and then the mechanical side has been dominating because its speed has greater than the synchronous speed. That's why in that case, it will start working as a generator. Rather than taking power from this direction, it will start providing power in this direction. Everybody see? Then power flow, the real power flow, feed direction will be towards the grid when the slip is negative. And how is it possible? With the help of some source. If you can somehow increase the speed of the rotor, this means if you can make this condition, that time you will call it three-phase induction generator. And in that case, you see the active power flow is in this direction, but still there will be some Q flow towards the motor. There will be some Q flow towards that direction. So this means if I draw this on, when it is motor, everybody see my drawing. When it is motor, this means it is taking both P and Q from the grid side to the motor. When it is induction motor, it is drawing both Q and P, both real power, reactive power. Why it is drawing the Q? Because there is no physical magnetic pole, unlike the synchronous generator. You have to create magnetic pole. That's why always it draws the reactive power. And why I am emphasizing this one? Because these are basically the coils. Coils means they will mainly draw the reactive power. So this is the motor diagram, power flow diagram in both this direction. This means from the grid point towards the motor. This is the indicated direction of the P and Q. But if it is generator, see this one, as I said, the power flow will be from the generator to the grid. So therefore P direction will be this, but still Q direction will be the same as the previous. Sorry, still the Q will be the same as the previous situation. Still the Q is this one, from the grid to the motor. Therefore everybody see, this means Q when it is motor operation, then from the grid to the motor. When it is generator operation, is still from the grid to the machine side. That's the difference is in the P. Could you follow me, everybody, what I am telling?
Yes, Dr. Ali, can you explain it again? Because I lost your voice in the middle about the Q, I mean the direction of Q.
Oh, okay. So therefore, when it was motor, everybody see, I started by telling that the power flow is from the grid side, I mean from the some source to the motor, right? Yeah.
Mm-hmm.
So this means in that case, this is for the motor. So this means if I say that this point is the source or the grid point, from the grid point towards the motor, both P and Q, both real and reactive. That's why you see the my arrow for P and Q. When it is generator, as I told you that when the sleep will be negative, it will start working as a generator. At that time, real power flow is towards the grid. So look this one, power flow direction, real power flow direction is from the machine to the grid side. But still the reactive power flow is in the same direction. Because still you have to produce the magnetic field to work as a generator. Do you understand?
Yes.
Manoj is fine?
Yes, Dr. Ali.
Yeah. So therefore, look the Q direction, irrespective of the motor mode or generator mode, Q direction is always from the grid to the machine. Just the direction, the opposite direction for the P. In case of motor, real power goes from grid to the machine for generator operation, because you know it is generator, so the function of generator to provide power. That's why the real power direction is from the machine to the grid. This is very important to keep in mind. This means the Q reactive power is very dominating for the principle of for the operating principle of induction motor. You must always provide the reactive power. But can you guess?
Excuse me, sir.
Yes.
Sir, in case of induction generator, the reactive power is needed continuously to like pump back the active power.
Yes, always you need, because you need magnetization. You have to magnet.
Okay.
There are no physical poles here. So
Yeah.
that's why always you need the Q. And it is
Because
called,
we are using the
sorry.
yeah, yes, sir.
And it is called the Q because these are basically the coils. So therefore coil will absorb the reactive power. Now the everybody see, what is the problem with that Q? As you understand that Q reactive power is needed to produce the required magnetization. Otherwise the system will not work, whether it is motor generator. So what will be the drawbacks, or what will be the consequence of drawing the Q always? So
Low power factor.
Low
There-
power factor. Very
yeah.
good. There will be low power factor. So therefore, the voltage might be low at the terminal because of having the low power factor. So what you have to do? You have to put some compensator at the terminal. That's
Capacitor gains.
exactly. That's you have to put capacitor. You have to put capacitor. That will compensate the reactive power. So that is the necessity of putting capacitor at the terminal of the induction machine. So everybody, like I will be asking you this question, why it is needed to put the capacitor at the terminal of the induction machine. So therefore, that thing you told, because without the capacitor, it is always drawing reactive power. So this means it is providing low lagging power factor. And what is the consequence? There will be voltage drop, but you have to maintain a steady voltage at the terminal. Therefore, to compensate the low lagging power factor, in other words, to maintain a steady voltage and to improve the power factor, we have to put capacitor at the terminal. That will be the answer. Okay, so I think everybody is fine. And then now move to the other two component. Then we can start the other things. Okay, so I think we are in this slide. Therefore, see the next one. Now, can you everybody? Oh, so you see, this is three-phase induction or asynchronous generator. Sometimes everybody keep in mind, three-phase induction generator, sometimes it is called asynchronous. So the meaning of the word synchronous means the always having the same speed. That's why the name was synchronous. Asynchronous means speed is not the same. Speed is not the same. Sorry. That's why
It's
sometimes it is
variable.
called. Yes, Venkat?
Yeah, it's variable speed.
Yes. So induction motor and induction generator both have the like variable speed. And that is the reason you see, I was giving you the example, let's connect a wind turbine, because the realistic application for the induction generator is with the wind generator system. That's why for most of the wind generator, they use the variable speed induction machine. Although there are some synchronous generator application, but mostly all over the world, they are the three-phase induction generator with the wind turbine. And then I think I have written down all properties here. You see, Manoj, look this bullet, number 4. Three-phase induction generator provides real power to the grid, but always draws reactive power. Slip is negative. Capacitor is connected to the terminal of the generator. So these are the properties. Okay, now moving forward. Sorry. Now look the synchronous motor. I think this will be the last item of the machine. Then we can start the stability talk. Everybody first look what I have written, synchronous motor. Again, the structure is very similar to the synchronous generator. So there is armature or stator on which the coils will be wound or mounted. Then there is DC field. It is rotating and it's called the not self-starting. So damper coil is needed. This is on Newton, damper coil. So I am coming to that point. And then I said, in case of permanent magnet synchronous motor, the DC field is permanently magnetized. I mean, same thing, same situation as to the synchronous generator. And then I just said on things, synchronous condenser under overexcited mode and light load condition, it works as a capacitor. That's why it can be used for power factor correction or improvement. Now, just let's have a look that person through that whiteboard. Okay, again, erase this thing, and then you all will be fine. Okay, so that everybody. So once again, This is North Pole, and then here it is South Pole. This is the rotor body, and then this is the shaft. And again, you see, similar to the uh, three-phase induction motor, apply the three-phase voltage here. So if you apply the three-phase voltage, like A phase, B phase, C phase, then there will be a rotating magnetic field. Exactly same thing as to the induction motor. So there will be rotating magnetic field. This is that phi s, but the difference between this one and the induction motor, here you see, although I have placed North Pole and South Pole, but I did not place any coil on the rotor body. So there is no actually winding except the damper winding. I am coming that point later. Initially, you see, there is no coils placed. So therefore, even though this phi s is being produced because of the application of three-phase voltage on the three sets of coil mounted on the stator body, but it is not building any voltage. So this means there is no interaction. But what will happen, everybody look now, everybody follow me, because initially that rotating magnetic field phi is being developed. What is the meaning of that one? This means inherently North Pole and South Pole is being created because this is moving and that is moving. Initially, you see this North Pole and South Pole is fixed because the motor has not started rotating. It is not rotating initially. It is static. So therefore, this North Pole and South Pole, which are the physical poles, these are not moving. But the internally, inherently generated North Pole, South Pole, that is moving. So everybody see, when this North Pole, I mean the externally generated pole, will be aligned with the North Pole, what will happen? North Pole will repel. So therefore, because this is moving in this direction, therefore this North Pole, what it will do? It will try to move in this direction. Same thing, at some point when the South Pole will be aligned with this North Pole, if it is South Pole here, then what will happen? North Pole, South Pole will attract. Because this South Pole, North Pole are like moving, so therefore this North Pole will try to move in this direction. Therefore, it will try to move, but it will not continuously start moving. Can you guess why? Because, because it has inertia. It has a certain mass. Initially, it cannot overcome the inertia. So just little bit, it will this direction or left side or right side. It will just little bit oscillate or vibrate, but it can make rotation because of the inertia. But this field is continuously moving. So therefore, because it is not moving, this means there is no proper interaction. So because there is no proper interaction, hence this shaft will not rotate. So that's why it is called that synchronous motor is not self-starting. It cannot self itself. So this means then what is the goal of this one? If the motor does not start and I am discussing the synchronous motor, then what does that mean? So we have to make it rotate. So therefore what is done? Let's put an extra coil, which is called the damper coil on this body. Why I put that one? Because already because of the application of three-phase voltage that phi s is developed, stator, and that is moving. Now there is onset of coil on this body. What will happen? This magnetic field will create voltage on this coil. You see, the before there was no coil, but now I put a coil, there will be voltage, and consequently there will be current flow. There will be another flux, and let's designate this is like phi d because this is the damper winding. So therefore there will be interaction between phi s and phi d, and then the torque will produce, and this will start moving. And then at some point what will happen, because this is also moving, when the South Pole will come nearby the North Pole, then it will be attracted because it is the opposite pole, and then it will be locked and it will be synchronized and it will start rotating permanently. That's why it is called with the help of damper winding, synchronous motor gains the speed or achieves the speed. Everybody, could you follow me?
Yes, sir.
Manoj, is this fine?
Yes, Dr. Ali, yes.
Yes. So therefore, you need the help of damper winding. Keep in mind, initially there was no damper winding. But in case of induction motor, from the beginning, there are 3 sets of coil. And this is the extra arrangement. And then once the motor has started rotating, everybody see, once the motor has started rotating, is there any role of this coil? No, there is no role of that coil. It does not matter, but initially you need it. Yeah. So that's why it is called the starting coil to start the synchronous motor. Okay, so I think then everybody understood. Now move forward. Okay, so we are in this one. Now from now on, actually, we will jump into this course. Yeah. So far, just we highlighted. It was just the rehearsal or the recap of the previous thing. Okay, now introduction to the system stability problems. So today we'll be discussing basic concept of stability, and then types of stability, and then followed by some questions or the problem. So probably we'll not get that much time, but so let's see so how far we can go. Now, everybody remember this equation, which is called swing equation. I was showing you in the previous class that phi A equal to phi m minus p. That is the one important equation. For many times, almost kind of every day, I will refer to you this equation to explain and to answer many questions. Frequently, I will be using and I will refer to you this equation. So therefore, what does that mean? Phi m is the mechanical input power, phi is the electrical output power, and phi is the accelerating power. And as I told you that phi m is that is coming from the prime mover, from the turbine, and P is your electrical output from the synchronous generator. Now, in ideal condition, phi m is phi, assuming there is no loss in the system. That should be 0. But what I said here, you see, phi can be changed due to any fault or load change. As I told you in previous class, in real practice, always kind of some change. So therefore, PM and P are never ever equal. Always there is someone like injecting power, someone taking out power, you're turning on light, turning off fan, etc. Continuously it is changing. Therefore, always it has some value. Now the thing is that P can be changed due to any fault if it is any short circuit in the network side, whether it is distribution and transmission, meaning that P will be significantly reduces or significantly low. It might go even 0. But we are assuming that phi m is constant because that is coming from the turbine. Assuming that there is no disturbance, no issue with the fuel input, turbine is properly running, consequently shaft is properly running. So therefore there is no lack of mechanical power. So issue is with the phi, electrical output power, because there might be fault, there might be load change, there might be some other problem. So therefore this is the governing equation. With the help of this equation, we'll try to understand the stability problem. So that's why everybody, you will be keeping in mind this equation. This is called swing equation. Now, because I mentioned the fault, first of all, see what is that fault? And then we will look some definitions of stability. What I have written here, everybody say, following a fault, temporary or permanent, in a power network, the system might be unstable or oscillating. Now, depending on the situation, depending on the type of the fault, system might be fully unstable or could be oscillating. So, and then here you see, I have written down the types of fault: three-phase to ground fault, which is called by symbol 3LG, three-phase short circuit, 3LS, double line to ground fault, 2LG, line to line, 2LS, and single line to ground, 1LG. So therefore here I like to I again take you to that whiteboard for a moment. Okay, let's erase these things. Okay, so for example, you have your generator that we are discussing, and you are looking the voltage profile, or you are looking the speed profile of the generator. And as you know that it is the synchronous speed, so this means the speed is constant from the zero time it is going on. Similarly, for example, as I said, it is producing 11 kV. Assume that that is also the constant, it is running. Now, for example, suddenly some fault happened. It is short circuit, open circuit, or single line to ground, or double line to whatever. Then typically what happens in case of any fault, typically voltage go downside and then tries to come back and it oscillates and then it settles down. This means it matches with the original value. And then speed typically goes high and then come down and oscillate, it settle down. But you see in the previous slide I said, due to any fault in the network, whether it is temporary fault or permanent fault, system can be unstable or can be oscillatory. Everybody see in this case, this was my desired, this was the steady state of the balance value. At this point, some fault happened, that is at time t. Then this time is t. At time t, some fault happened. Consequently, voltage went down. But then there is some oscillation. After some oscillation, it came back. So that you will say this system is stable. In this case, omega speed went up, but then came down and oscillating. Again, it came back. But if it was the situation, okay, it came down, it came, and then it is doing, and it is continuously oscillating. This is the example of unstable system. Or this speeded up, went down, it is like that. This is the unstable example. So, I mean, because there is continuous oscillation. So the system is not stable. Here you see that because voltage is continuously fluctuating, not stable, oscillating, so the customer will be impacted. Even sometimes depending on system or the nature, property of the network, it might happen. Like you see, can you see? Gradually I am increasing, like fully unstable. And with high main, same thing it might happen. So and you see, this is the speed. So what will happen to the shaft? Can you guess? Can the system sustain? No. The shaft will be damaged. So therefore, these are the unstable situation. So therefore, in this class, like we are looking power system stability, meaning that we learn that okay, there can be fault, there can be some oscillation, but after some oscillation, it come back to the desired position. In case of the voltage, in case of the speed or the frequency, it may go high, let go come, after some oscillation, it come back. Therefore, now as you can see, depending on the fault, it might automatically come back to the original position. Sometimes it does not come back. It depends on the severity of the fault. If it was like that, then there will be high peak here and there will be this, it might not come back. That's why you must need to put some control means, stability control means. Your goal is that to maintain stability always in the system. There can be fault, yeah, because you don't know the when and what type of fault, where, what is the location, is it nearby your house or on the distribution or transmission line? You don't know, and you don't know the nature of the fault. But you have to put some control means to mitigate the effect. So what is the control means? Meaning that, for example, it was going down, immediately if you have a controller, it can detect that voltage is going down. Okay, try to maintain. So maybe if you have controller, immediately it will be stable. You see, or in this case, if you have a controller, it will detect, maybe it will go like that, and then immediately it will be stable. So this means this result in stable situation. I mean, it is not, there is no controller that can immediately maintain the stable, this situation. It is not possible because every controller needs some time to understand. There is always time delay and you have to actuate the circuit. So that's why always like in that way it works. And then versus you see when there is no controller, continuously it is oscillating, and as I said, depending on the network, it might be fully out of step, out of synchronism. So now this is the meaning of the stability or instability. And I think I was mentioning various types of faults. So let me just clean this portion. So now look this one. For example, we have 3 line that FH, BH, CH. So and now let me clean up this thing. So in the previous slide, so those are written. For example, type of the fault is 3LG. What does that mean? 3LG means it is sorting all 3 phases, see, and then it is grounded. This is the grounding. This is the land or soil. So therefore, what is happening? All 3 phases somehow got short-circuited. It could be on the transmission line, distribution line. If you have a 3-phase load, it might be at your home or in industry. 3-phase shorted and then ground. So mainly this happens on the distribution and transmission line. This one, it is called 3LG fail because it involves all 3 phases. So therefore, the best example is that, for example, on a stormy day, a tree has fallen and this is the root of the tree, and then some branch are touching all 3 phases. And because tree is a, the good conductor, it has the leaf that has the juice or the sap, so it causes the short circuit, and that is very dangerous. So if this is the situation, then again, like if you go back to that equation, what will happen? Phi equal to Pm minus P. Under this situation, because this is short circuit means the voltage is 0. So therefore, what is your P? What is P means? P means your multiplication of voltage and current. Whatever there is power factor, but first thing is the multiplication voltage and current. So what is happening? It is going 0 or close to 0. So consequently, your power value, P value will be 0. So then what is the accelerating power? Pa equal to Pm. So what will happen? Your generator was running at this speed, it will very speeded up. It will happen. And if the speed goes very high, the frequency will go very high. That is the impact. So anyway, this is the example of 3-phase to ground fault. And then next is 2LG. It is called double line to ground. What is the example? For example, 2-phase got shorted and then grounded. For example, I am drawing the other side, although this is above side, then let's assume that, okay, this is the grounding. So this is the example of 2LG. So this is the example of 3LG. And then next it comes 2LS, or sometimes simply it is called L2L. This means line to line fault, meaning that it is just 2-phase shorted. It is not grounded. So this is the 2LS. And then other thing is called on LJ. This means that there is on phase that is grounded. This is frequently happen. These things frequently happen. There can be other things, simply 3L here. Number 2, 3LG, 3L. Just 3-phase shorted. This means the best example is that it is not that tree has fallen, like as an engineer, you are working on the lines and somehow you made a mistake and you created some short, or a bird, like a red bat, whatever, some birds were flying. And many times I think you have seen that especially the bat, that animal, got trapped. I mean, it created short and then got died. Yeah. So that is the 3L, or sometimes it is called the 3LS. So now, according to severity, this is the ranking.
Excuse me, sir.
Yes,
Sir, what is this LS? Actually?
sorry.
What is LS?
Oh, it is called it is called 2LS, means just the two lines,
Yeah, I got it.
two lines, or sometimes it is called LL. I mean, both symbols are
Line to line.
line to line, or sometimes in the letters 2LS, this symbol is also used.
Yeah, sir. Thank you.
Yeah. Or in this case, like I have written 3LS, sometimes 3LL, it is also used in literature. And then 3-phase to ground, it is called 3LG. If you see the word letter, the G, this means that has been grounded. So therefore, these 5 types, 3LG, 3LS, 2LG, 2LS, 1LG, this is according to severe range. Like this is the least severe, then a little bit severe, more severe, more severe. This is the most severest one, 3LG. So therefore, how do you understand that? Therefore, for example, you are looking at speed profile, for example. So therefore, for example, initially speed was fine, short circuit happened. If it is 3LG, then speed might go that high, for example. If it is 3LS, then speed might go at that level. I mean, see the difference. If it is 2LG, it might go at that level. If it is 2LS, it might little bit severe. It is 1LG, very little effect. You see? Therefore, this is the severity ranking. So therefore, everybody, please you will remember this ranking. Ranking means this is the most severe, this is the least severe. Now the top two, because top two involves the all 3 phases, accordingly, these two are called the balanced fault or symmetrical fault. And the bottom 3, 2LG, 2LS or LL1LG, because they involve either 2 line or only 1 line, that is called unbalanced fault or unsymmetrical fault. So everybody, could you follow me?
Sir, could you
Dr. Ali?
repeat one?
Yes,
May I ask a question, please?
sure.
So you remember last class when you talked about the double transmission line?
Yes.
In that case, if all line cut off, we will call it 3 line to ground, or it's like we're gonna treat them separately?
That is separate things. So you are talking that double line to, I mean, double line circuit somehow fully off, right?
Yes.
Yeah, that is the, that major mishap in the system, major calamity in the system. For example, there was a storm and every pole got damaged and broken down and line got disconnected. So in this case, we are assuming that, okay, the lines are in that way. And then, for example, what you are talking, let me clean up this one. Like you are talking about these things. For example, this is on 3-phase, there is other 3-phase, and there are some storm or tree has fallen and grounded. But this side is fine, or for example, this side has also been grounded, yeah. Like it is fully collapsed. So therefore, this is like major blackout situation. Got it? Yes.
I got you.
Okay.
Thank you.
Okay, thanks. Okay, I think everybody understood. You will be, please, everybody, you will be remembering this severity ranking, because in your assigned paper or in some literature, you might find the single line to ground fault. That will be, okay, this is the least severest one, and this is pretty common. Like 3LG and
Excuse me, sir.
3LS is, yes?
Yeah, what are those 3LG? Those are unbalanced faults?
No. Top two are the balanced fault.
Okay.
3LG and 3LS or 3 line to line fault are called the balanced because it involves all 3 phases. So all 3 phases have equal impact. That's why that is the balance. Yeah, balance.
Or symmetrical, right?
Yes, or symmetrical. So before, the last class we are looking the definition of balanced and unbalanced three-phase system, or whatever it is, delta or Y connection. But even though it is fault, it is creating fault, whether it is 3LG or 3LS, because it involves all three phases will have equal impact. So therefore it is fault means current will increase, voltage will go down, but they will still maintain the proper 120 degree. So that's why it is called the balanced fault, because all three phases have been affected equally. So there will not be any change in the phase difference. Got it? Yeah.
Yes, sir.
But in this case, look the bottom three, like 2LG, 2LS, 1LG, because like number 3 and 4th case, 2 line is involved, one phase is healthy, one phase is intact. In this case, 2 phases are fine, only one phase got affected. Let's say only one phase. It could be any phases. And that is creating unbalanced in the system. For example, because fault is only one fault, two phase has properly, for example, 120 volt, 120 volt, but the third phase has voltage close to 0. That is creating unbalanced. Or in this case, two phase voltage has changed, only one phase voltage is maintaining 120. That's why 2LG, 2LS, 1LG called unbalanced or unsymmetrical fault. And
Yeah,
top two are the most severest, but those are called the balanced fault. I mean, unbalanced, now this unbalanced fault had a different impact. As I was telling you, I mean, in terms of severity, these are the less severe, but they have negative effect. They have the drawback. What is the drawback? There will be zero sequence current that will flow through the neutral. So the neutral will be affected. So in this case, it is balanced fault. So still the neutral is fine. But in this case, current will start flowing through the neutral. So in that sense, and then this has more like detrimental effect or the negative effect. Okay, so now moving forward, I think we can go a little bit more. So you see this slide, here are the types of fault. I have written the full meaning: 3LG, 3-phase to ground; 3LS, 3-phase short circuit; double line to ground fault; line to line fault; single line to ground fault. Yes. Someone is talking? Yeah. Could you turn off, could you mute your phone? Okay, now see the definition here. What is the power system stability? Everybody see. I have written it may be defined. Okay, see the full screen. It may be defined as that property of a power system which enables it to remain in a state of equilibrium under normal operating condition and to regain an acceptable state of equilibrium after being subjected to a disturbance. So this is the definition of power system stability. This means under normal condition, system is at equilibrium position. System is at balanced position. In real practice, as I told you, although there are always little change in a load, but still if that is in equilibrium condition, that is an acceptable condition, then that is the stability. Or there is major disturbance, but then after some oscillation, system came back to the original position, but to an acceptable state of equilibrium, even though it may not fully come back to the original position, still that is called the stability state. So that is the definition of power system stability. This means there might be small signal stability issue, and then there can be major disturbance. In both cases, if the system come back to an acceptable state of equilibrium position or full equilibrium position, this means the system is maintaining the stability. If not, then the system is unstable. Now, there are 3 types of stability. One is called rotor angle stability, other is called voltage stability, third one is called the frequency stability. Although all are like interrelated, and very, that nearby, but still the literature distinguishes them. Rotor angle, voltage stability, frequency stability. So what is the meaning of rotor angle stability? It is the ability of interconnected synchronous machines of a power system to remain in synchronism, mainly to maintain same frequency and speed. So it is the rotor angle stability, meaning that there can be many synchronous machines, 10, 20, 50, 100 in an interconnected system. But if they remain in synchronism, what is the meaning of synchronism? They are maintaining the same frequency and speed. All are maintaining 60 hertz. All are maintaining, for example, 3600 RPM. Then you will be telling that those machines are stable in terms of the rotor angle. That is called the rotor angle stability. And now this rotor angle stability is two types. One is called steady state or small signal stability, and then one is called the transient stability. So see the definition. It is the ability of the power system to maintain synchronism under small disturbance. What is the meaning? That small variations on load, small variation in generation, sometimes not only the load side, although in rare cases, in generation side, in power plant, there can be little change. For example, because of excitation or because of some little input variation of the fuel input. So if that is the change, and if the system maintain a acceptable equilibrium position, that is called steady state or small signal stability. So I think I want to stop here so that like you are not fully bored. So we will continue from the next slide in the next class. So is this fine?
Excuse me, sir.
Yes, Dr. Ali.
Yes.
Could you please repeat power system stability?
Okay. So see the definition. For example, you have some small change in the system. You changed a small load. In real practice, always a small change is being happen, especially the load. And because of that load, if still the system remain in an acceptable equilibrium position. Equilibrium position means if you see the voltage, for example, at your home, it is properly maintaining 120. If you see the generator speed, it is properly maintained 3600 RPM. Because of the small change, there can be small change in voltage and frequency and speed. But after some oscillation, if the system comes back to an acceptable position, acceptable means there is a particular range. If the system goes beyond that point, then typically it does not come back. It is called the unstable situation. So therefore, because of small change and because of large change in both cases, if after some oscillation or after some change, if the system means voltage, frequency, rotor angle, speed, everything is come back within a acceptable range, then that is called the stability. This means the power system is stable. Is this fine?
Yes, sir.
Yes.
Okay.
So therefore, see the definition. It may be defined as that property of a power which enables it to remain in a state of it. Now the question is, definitely, although continuously some load is being changed in the system, in the power system, there are some sophisticated controller means. There are a lot of primary controllers. When there will be any major fault, then there are external sources, external control means. We will be covering those things later. But inside the system, what are the primary control means? AVR, automatic voltage regulator. What is the other means? Governor. What is the other means? PSS, power system stabilizer. So there are some internal or primary control system equipped with the generator, power plant, and throughout the network to maintain the stability of the system. That's why it says it is defined as that property of a system which enables it to remain in a state of. How it will remain? With the help of those components of those controlments under normal operating condition and to regain an acceptable state of equilibrium after being subjected to a disturbance. In this case, disturbance means the major fault, 3LG fault or 3 line to ground fault or double line to ground fault. That is the meaning of disturbance. Disturbance is not like small things. And then if the systems come back to an acceptable state, then you will say the system is stable. And that is the definition of power system stability. So is everybody fine?
Yes, Dr.
Yes, sir.
Okay, thank you. So today, I like to conclude here because it has been 7 p.m. So we'll be continuing in the next class. And then we will be talking much more about the stability, various definition, and gradually we will go deeper and deeper of the stability issue. Okay, so I'm stop sharing.